Hello friends, this video on alcohol, phenol and ether part 26 is brought to you by examfear.com. No more fear from exam. Let's talk about ethers. To start, let's talk about the preparation of ethers. We'll prepare ethers by three methods: by dehydration of alcohols, Williamson synthesis and the Grignard reagent. Let's understand the first method, that is dehydration of alcohol. So here you generally get symmetric alcohols. Symmetric ethers. So you heat the alcohols with H2SO4 or H3PO4. For example, I have ROH. I heat this with H2SO4, right? I get ROR. That's what the reaction. So we'll see the mechanism for this. For example, you take 2C2H5OH, you react with H2SO4, you get C2H5O, C2H5 and a water molecule. Correct? This is diethyl ether. Correct? So this is my preparation by dehydration. The name dehydration means you remove water molecules. So from you take two alcohol, from one you remove OH, from one you remove O, you get dehydration. Please be a little attentive here, because if you have alcohol and sulfuric acid, you have to maintain a specific temperature. That is my 413 Kelvin. If I raise the temperature to 443 Kelvin, it gives alkene. So we'll see the reaction mechanism for this. I have, let's suppose, CH3, CH2, OH, and I have H plus here, right? H plus from sulfuric acid. So this goes here. What you get is CH3, CH2, OH. H, and since oxygen has given electron to H, it gets positive charge. Correct? Now this reacts with one more CH3, CH2, OH. Now this is a positive charge, this has a lone pair of electrons, it will react. And the whole H2O will come out actually. This H2O will come out there, and here it's a positive charge actually. So with this, what you get is CH3, CH2, and this OH will also come out. O, CH2, CH3. Correct? You can form the carbocation also if you want. You get plus charge here, and this H comes out, you get minus here, and forms a bond. There's a limitation, it is only for primary alcohol. Why? Because for secondary and tertiary alcohol, if we are not able to manipulate the temperature, maintain the temperature, you may get alkene. Right? Only for 1 degree alcohol, and only for symmetrical ethers. Only for 1 degree and symmetrical ethers. Because as I told that you have alcohol and you get this sulfuric acid, you make the temperature as 445 Kelvin or something, you get alkenes actually. Right? You don't get ethers. So the disadvantage of this method is it is only for primary alcohol and primary alcohol and symmetrical ethers. So we'll try with Williamson synthesis now. So you can make secondary or tertiary ether also here. So here this is a nucleophilic substitution. We'll see this. What happens is I have my RX, let's suppose my primary alcohol here, and my RONA, that is my sodium alkoxide, this is my primary, and this is my tertiary. What I get is ROR plus NaX. This is my Williamson synthesis reaction. Please note, this Rx has to be primary. If it is secondary or tertiary, then in that case, elimination reaction competes over substitution. correct? And this is good to have tertiary. So let's see this reaction here. So this is minus, this is plus. So this minus, this is a nucleophile actually, 8O minus, RO minus, will attack this R and this X minus will come out. So with this you get, and let's suppose this is R dash, so you get R dash OR plus NaX. So this is how it works. It's a pretty easy reaction actually. So we'll take one example. CH3, C, CH3, CH3 O minus Na plus. This is tertiary I took, and I took a primary alkane here. So what happens is O minus will attack this, Br minus will come out. So what you get is this compound CH3 O CH3. Let's see what happens if you just reverse the effect. In fact, say CH3 O minus A, and here instead of primary you take tertiary, right? You see the effect now. Now as I told, if you take secondary or tertiary here, you have elimination reaction. Let's see what, so this O minus has to attack, right? But if you see there is no place to attack. So instead of attacking this carbon, it will attack any of the hydrogens. So if you see this CH3O minus is a strong nucleophile and strong base also, right? So if due to steric hindrance, if it is not able to act as nucleophile, it will act as strong base. It will pluck out this hydrogen from here, and what you get here is so it will have elimination reaction. So please note, in this Williamson synthesis, my alkane has to be primary and my sodium alkoxide has to be secondary or tertiary. The next reaction is Grignard reagent. This is used to form a higher ether from lower ether. So I have a lower ether already. I want to form higher ether. I can form using Grignard reagent. For example, I have, let's suppose, this guy ROCH2X, and then you have RMGX. So when you react this, you get ROCH2 instead of X, the whole R thing is attached here, right, plus MgX2. This is my bigger ether. If you want to take one example, CH3O, CH2Cl, if you see the small ether, and here I'll add this guy, Grignard reagent. So what will happen now here is this Cl and this thing will come out. You will get CH3O, CH2 instead of Cl. I get CH3 here, and I get Mg BrCl. This is a typical reaction. I won't go for the reaction mechanism because we have seen so many Grignard reagent reactions, pretty easy. See, this will have slightly negative charge, this whole thing will have slightly positive charge. So this will attack this carbon and this chlorine will come out. Correct? So it's again a nucleophilic substitution. Let's take some numerical now. The question says the following is not an appropriate reaction for tertiary butyl ether. So we have seen just now, this is minus Na plus, this is my nucleophile which want to attack, but since there is no place to attack this carbon, since it is a strong nucleophile and strong base both, so it will attack this the one hydrogen here, it will pull hydrogen here and chlorine from here. So it will go for elimination reaction. What product you will get is something like this. This is what you'll get. Right? So this is not appropriate, and this is the product. Suitable reaction, you make this as primary and this is tertiary. So what we can do is we can just flip this. We can make it CH3, C, CH3, CH3, ONA, and here I can make it C2H5Cl. Now with this, it will be minus, and this will be minus here. So what will happen now is, now this reaction will happen. This O minus will keep this. And with this you will get what you are looking for. O C2H5. Correct? So this is what we will use. Else this will be the major product. The next reaction, we write the names, the reagent and the equations that is used for the preparation of the following ethers by Williamson synthesis. So we have to prepare 1-propoxypropane. So let's see what is 1-propoxypropane. Taking this in red. Propoxypropane. This is my propoxypropane. Now to prepare this using Williamson synthesis. So I will take some ONA and one as RX, right? RONA and RX. So this I can take as RONA, this I can take as RX. So what I am supposed to take is Na plus RX. And if you do a Williamson synthesis on this, you get what you want. Plus Na X. This is not RX, this is X. Let this be Br. Let this be Br. So you will get NaBr. Correct? So this will be sodium propoxide and this will be 1-bromopropane. The next is 1-ethoxybenzene. So the product output is this guy. H5. So I can put this with halide, this portion with halide, and this portion I can put with ONA. So what you will get is this with ONA and this small portion, the primary alcohol with halide. This is bromoethane, this is sodium phenoxide. When you go for a Williamson synthesis, you get OC2H5 plus NaBr. Correct? Again, let's take some more examples. We have to form, again using Williamson synthesis, 2-methoxy, 2-methylpropane. 2-methoxy, 2-methylpropane. So first let me have propane with propane, right? And at 2 position I have a methyl, 2-methylpropane. And at 2 position I have a methoxy, OCH3. So I have to form this. So one side I have tertiary, one side I have primary. Obviously primary I'll take with some halide and this tertiary I'll have to take with ONA. So the reaction has to be something like this. ONA and this part is CH3 I have to take with halide. Let me take with Br only, right? So with this what you get is, correct, this is 2-methoxy, 2-methylpropane. So this is my bromomethane and this is my sodium 2-methylpropoxide. Let's see the other one in red. 1-methoxyethane. Let's me first draw methoxyethane. So I have methoxyethane, ethane, and then I have a methoxy. This is the one I have to form. It's pretty easy actually. So this I can, the bigger one I'll take with Na and smaller one I'll take with some halide. So I'll get something like this. Na plus Cbr, I get this with Br. You can add hydrogens, extra hydrogens, right? Example, here you have to add these hydrogens. Here you have to add hydrogens. So we can add this extra hydrogens. Correct? This is my sodium, this is ONA actually, sodium ethoxide. This is bromoethane. The question is 1-propoxypropane synthesized from propanol. So propanol is my input and this is nothing but methpropanol and 1 propoxypropane, and I have propoxy. I have to form this from this. So if you see, if I just add these two and remove one water molecule, I'll get this. That means if I go for a dehydration in the presence of some sulfuric acid or H3PO4, anything I can take, I'll get this reaction, right? So this is my reaction. This is my, I'll take 2 of these with some H plus, I'll get what I want. That is 1 propoxypropane. Correct. The reaction mechanism, if you want, you can just add this guy here, this O, the lone pair will attack this H plus, right? Deprotonation will happen, right? Deprotonation will happen, and then the other guy here, this lone pair, right, will attack this carbon. Sorry, not this. One more I'll have right here. So this guy will attack this carbon. And thus with that, H2 will go off and this hydrogen will also go off and will form this 1 propoxypropane. We have seen this mechanism in the previous slides. If you have doubt, you can just refer that. So first is the nucleophilic attack, and then first is the protonation. Once protonation is done, then is the nucleophilic attack. This guy is the nucleophile here. This will attack this, right? And then I have a deprotonation. I'll remove this extra hydrogen actually. This hydrogen, you'll remove it off. 3 steps. Let me draw it. So let me write the mechanism green now. Okay, the first step, as I told, was you have this and this, you have this H plus protonation. This will come here. So what you get is this with OH, and oxygen will get a positive charge. Correct? Now there will be a nucleophile. The nucleophile is nothing but my propanol here. This will be attracted towards this positive charge. Or I can do it, remove H2 from here. I can remove H2 from here. This carbon get a positive charge. It will get attracted towards this carbon here. So with this, what you get is CCC, O, CCC and H. And with the positive charge on this, oxygen, because this oxygen is losing electron, right? So this gets negative, positive neutralized, and this gets positive charge. And now to lose this positive charge, this hydrogen will say, okay, I'll lose my electron, I'll get rid of U, and this H plus will go and this charge will go off from here. Correct? This bond will break into positive and negative was neutralized, and this positive H will go off. So this is my SN2 reaction. Why? Because the slow step is this step, right? When this my propanol itself is a nucleophile. The next is preparation of ether by acid dehydration of secondary or tertiary alcohol is not suitable. Why? We have discussed that if it is secondary or tertiary alcohol, then what happens? Elimination takes place. Correct? Because it's all SN2 mechanism. Correct? So it should be unhindered. If it is hindered, then we have elimination. So elimination reaction competes over substitution reaction here. So if it is tertiary or secondary, then elimination takes the preference. Thank you. Visit our website examfear.com to watch more and more quality educational videos. You can also attempt free online tests that are there in our website. You can also get access to tons of free study materials, and you can also find free tutors and mentors in this website. Thanks a lot for watching.